I'm going to start a three video lesson over rational functions. Right? Rational functions are, we do have a parent function, I guess, for rational functions. And today I want to talk about just introducing them, getting a general idea for them, and getting a domain for them. Okay? So our most basic rational parent function is called the reciprocal function. And it looks like this, all right? It's the function 1 over x, and a couple of key points that it goes through that I'm going to be checking for is 1, 1, and negative 1, negative 1. And those big blue lines that go through it are called branches, okay? So they go through those points, and they get closer and closer to the axes, but they don't actually touch them, meaning we've got some sort of imaginary line that is making it so they don't touch, but it gets closer to it. We'll talk about those in just a minute. The other one that our book talks about is the reciprocal squared function. Squared function. And what they did on the reciprocal squared function was they simply squared the top and squared the bottom, and then it made it so that this branch that was in the third quadrant flip it to the second, and there are some other little minor differences, but the ones I'm going to be still checking for is that you're still going through the point 1, 1, and then this time negative 1, positive 1. We still have a vertical imaginary line right there that's approaching, as well as a horizontal one that's in the same spot. So those imaginary lines are called asymptotes. Okay, it's a really kind of a weird word to say, because you almost have to start off saying a bad word, and then suddenly you have to put an M, a P, and a T all right next to each other. So I'd sometimes say it too fast, and it sounds like a chemistry term, the asymptote. Okay? And so the line that was on my y-axis is a vertical asymptote. And we're going to be labeling our asymptotes in this video and in the next one with the equation x equals a. Okay? While a horizontal asymptote would have been that line that it approached as it went off to the left and right side of my graph, and we are going to denote that with the equation y equals b, or wherever b is. So I want to sketch a graph of the reciprocal function. The reciprocal function was that first one that had the branches in the first and third quadrant, but I'm going to move stuff around. Whenever I'm graphing a rational function, I always want to find my asymptotes first. And so these got moved. It got shifted 1 unit to the right, it says. So 1 unit to the right would be right over here. Draw my vertical asymptote there. You can think I'm moving my horizontal asymptote to the right one as well, but that doesn't move it. So that doesn't move yet. Up 4 units on the other asymptote, 1, 2, 3, 4. And again, you can think, well, I need to move this blue dotted line up 4 units as well. Well, it's still a line, a vertical line that's been moved up, does not change really its position since it goes on forever and ever. So a lot of people look at this and they say, oh, well, I see what you did. You changed your axes. Not really. I changed the imaginary lines that were on the axes. But if you want to think of it as changing the axes, that's fine. It's just make sure you get those. That will help you get your branches in the right spot. So I'm going to the right one and up one from this intersection right here, and then to the left one, down one from the intersection. And so my branches will move just as far as my asymptotes do. And so hopefully now that everything's on there, you see that we did just take that first graph that we talked about, and we moved everything right 1 and up 4. Oh, I'm sorry, it says to identify the horizontal and vertical asymptote. So I would like for you to tell me that this is at x equals 1, and the horizontal one is at y equals 4. Having those labeled on there, I think makes it look a little better. In case you miscount, I can tell where you meant to put it. So hopefully not take off too much. So I want you to try this one. Okay, go ahead and hit pause on this, and then come back and see what we got. All right, guys, this is what my graph does look like. Hope it matches. Now, just to formally introduce a rational function, okay, we did some very basic ones. As you can see, g of x equals 1 over x is one of my examples down here. But my definition of a rational function is simply a ratio of two polynomials. They said a quotient of two polynomials. That's fine. So what we're doing is we're taking these polynomials that we've been finding zeros for, been doing synthetic division with, that we just graphed earlier in the week, and we are looking at taking that polynomial, putting down a huge division bar, and then dividing it by another polynomial, known as p of x and q of x. Okay, and so some examples of them are down here. We already talked about g of x. Look at this f of x right here. Simply taking a linear function over a quadratic. That would fit the definition of what I have for a rational function. Taking a quadratic, we graph that quadratic that's up here on top over a quartic function. We graph the quartic function as well. What happens when we divide the two? How crazy is it going to look? Well, you'll have to watch some more videos to get to that. Okay. What I want to talk about is the domain. Okay. The domain of a rational function is going to be the set of all real numbers. I didn't mean to erase my graph a while ago. I'm going to go ahead and do a rough sketch of it over here to bring it back. 1, 2, 3, 4, 5. I even told myself while I was graphing it, Mr. Lovelady, do not erase this graph. You're going to need it in a minute. So it looks something like that, I hope. Maybe I counted wrong. I don't think I did. And so we talked about domain before when we did all the other parent functions like absolute value, square root, cube root, all of those. And one thing that we always told ourselves for domain, or I guess that we asked ourselves, is what can x be on domain? What can x be? Okay. And a lot of times we got negative infinity to infinity, and I assure you for rational functions, negative infinity and infinity both want to come into play, but we've got a little problem that's going to, we might have a problem or more than one problem that's going to come in between it. Okay, so looking at the domain of my last example over here, the domain, the smallest x value that I see this thing touches is, well, yeah, it's going all the way out to negative infinity. Okay, I'm good. I'm just kind of chugging along here, and all of a sudden, whoa, going straight up. Now remember, this guy does not touch -5. Okay, it gets really close to -5, but it doesn't touch it. So I just go from -5, and I show that I don't touch it with that parenthesis. We have the weird or sign that we use in math, and we pick up right on the other side of -5 right here. It got really close to it. And then if I trace my way down this branch, it goes all the way out to positive infinity. Oops, that's a 5. Goodness gracious. Goes all the way out to positive infinity. Sorry. And so my domains are going to look something like this tonight. Eventually, we're going to get to a point where we can graph these and do domains. But for tonight, I just want to find domain using the function notation. And it says that it's anything that causes the denominator to equal 0. Anything except those numbers. Something I think about with domain and rational functions is what will make my calculator say error when I'm dealing with a rational function? Or what makes my calculator say error whenever I am dealing with division right here? Well, dividing by 0. Okay, so I know that I do not want this bottom down here to equal 0. So if I bring that up, x plus 2 cannot equal 0. I see that x cannot equal -2 if I subtract 2 from both sides. And that is my domain. However, I'm going to be that guy that wants it in interval notation. So x can be anything in the world. I'm sorry, not anything in the world. Any real number, not getting into imaginaries, any real number other than -2. So it can be anything from negative infinity all the way to -2. And something's going to happen at -2 to make it so it's not defined. And then anything from -2 all the way to positive infinity. Now using the same idea for this g of x right here, I said it equal to 0. There's two things that's going to get in the way. First of all, if this x right here is a 1, that's going to give me 1 minus 1. which is 0. That'd make the whole thing go to 0. If we need to, we can bring it up here and work it out. X minus 1 equals 0. I guess cannot equal 0. But cannot equal on there. So x cannot equal 1. If I plug in a 1 in for this x right here, it makes the whole bottom go to 0, because 1 minus 1 is 0, and then 0 times anything would give me 0. But also on top of that, x minus 3 cannot equal 0. So x cannot equal 3 if I add 3 to both sides. So my domain for g is just a little bit longer. It's going to be anything from negative infinity up until 1. Make sure we choose a smaller number. Union with everything from 1. Well, I run into another bump at 3. I'm not allowed to touch 3 because that would make the bottom 0. And then anything from 3 to infinity, I'm good to plug in. Okay, so it still is negative infinity to infinity. I just have to cut out the values of 1 and 3. Okay. Let's try this other f over here. Okay, again, cannot equal 0. Now I could spend a long time trying to plug in different values for x that would make this go to 0. I could try 0. Nope, that didn't work. 1, 1, no, nope, that didn't work. It would take a long time. So instead, what I'm going to do is I'm going to try to make it so this denominator looks like the denominator on the previous problem with g of x. And so yeah, I'm going to have to factor. You might have to do some guess and check on it tonight. I'm going to have to get this thing worked down. But if I put a plus 4 here and a plus 1 there, 2 factors of 4, that to give me 5, that would work. Okay? But keep on forgetting my not equal to. So x cannot equal negative 4. X cannot equal negative 1. And I want this in step building notation. So anything from negative infinity to negative 4, negative 4, negative 1, negative 1 to infinity. This would be my domain. Notice on all these, I have not messed with the numerators at all. Numerator does not play with the domain just yet. It does not play with the domain in general, but we will be doing some stuff with that in the next video. All right, if you want to work these last two, you can pause the video, see if you match. If not, just fast forward to the end and get your homework if you think you got it down right. And there's those last two answers.